momentum right now. An impulse. So today, you obviously have the note available to you. So I would focus more on the things that I say today than the ones that are on the screen. Because I'm going to say a lot more than you're going to see on the screen. Not saying the screen's not important, but it's a little bit of both. So there are two concepts here, and both of these are brand new. One is momentum, and one is impulse. And you probably heard of momentum before in some sort of context, because it's really the math version of inertia. I'm just looking for my pointer. So, momentum, as I said, there's two types of momentum. There's linear momentum and rotational momentum. So, our class, we focus just on linear momentum, like going in a straight line, momentum. Some of you referenced rotational momentum in your last project for objects that twirl in the air. So, anything that turns has rotational momentum. And that's something you do in physics in university because you need to know calculus before you get there. So momentum has a very simple equation that goes with it. It's just as it says up there, it's a product of the object's mass and velocity. So we already know from like your intuition that heavy objects are hard to stop. And normally, or up until today, in grade 11 and grade 12 physics, so you related that to its inertia, right? Larger objects have more inertia, right? So today we're changing that a little bit because we're going to put the math to it and instead of calling things inertia, we're going to worry about its momentum. So when larger objects are moving and they're hard to stop, it's because they have a lot of momentum, okay? The equation for it, as I said, is a pretty simple one. And we'll do more math with it tomorrow. But just so you have it, momentum in math, or in physics, is given the letter P, which is obviously not related to anything that deals with momentum. So it's lowercase p. It is equal to, as it says up there, mass and velocity. So you have your mass and velocity. And it's not squared. So it's a very simple equation, 3 variables, 2 of them are multiplied together, no halves, no exponents. Pretty, like, in terms of equations, it doesn't get any easier than that. Keep in mind that the momentum is a vector quantity. So direction matters again. So only in energy do we take a break from direction stuff, and now direction's back. So the momentum part here, we're going to start off with just a simple equation. We're going to look at 2 objects interacting with each other, which is going to add a layer of difficulty, but they're going to collide head on and whatever it is. So that's what we're going to be at Friday. And then on Monday next week, we're going to not look at head-on collisions. We're going to call it, in physics, they're called glancing collisions. So that means they're not head-on, and it's going to be a 2-dimensional problem. So that's where we're going to go with this. So each day we're going to add a layer. Starts off with P equals MV, but then we're going to have 2 P equals MVs, and then we're going to have 4 as we get into 2 dimensions. So it gets very repetitive. So just make sure you ask questions as we go along. The units for momentum is also crappy because the units are kilograms times meters over seconds. There's no shorthand for it like joules or newtons. That's just what it is. Would it be nice? But there's not much there. Okay? So that's momentum. Any questions with that? So it's like inertia. You have experience with it, but now we're quantifying it with an equation. Impulse is a little bit different. Impulse is like work. So when you have impulse in a question, it's because an object's working on another one and it's changing its velocity, right? So when we have that change in velocity, now we have a change in speed. So you can read the words up here. But the connection here is that impulse is like work and the momentum is like energy. So when we talk about momentum of an object, we're talking about a singular thing. We're looking at how it moves. When we look at impulse, we're looking at two objects interacting. There really is actually Newton's third law of motion, and we'll show you how that kind of works out. Or I will. We use not the right term yet. So impulse is related to force from one object to another, and that force causes the object to change speed. We know that from Newton's second law of motion, right? A net force causes a change in speed or change in velocity, right? So this is just a different way of looking at the same idea, but through the eyes of momentum and impulse, and this has lots of applications. So the equation looks like this. Actually, I haven't read your textbook, so I don't know what they do. In the old textbook, it was delta P, which is change in momentum. So that's where it starts. In university texts, when I was in school a long time ago, 20 years now, we used the letter J, which is really weird because it has nothing to do with anything. But it was a vector quantity. So J stood for impulse, and probably still does. We're going to use delta P because that makes a little bit more sense because it's the change in momentum. And your other side of the equation is the net force times time. Okay, so this is kind of where we're going to stay. Just a different way of writing Newton's third law of motion. Conceptually, that shouldn't be much of a stretch for you, because you know that if there's a net force acting on an object, it's going to accelerate. The longer you apply that net force, the bigger the change in speed's going to be, right? Your change in momentum. So if I expand this a little bit more, just to kind of write it in a different way, maybe to help me see things a bit better, we know that change in momentum is always your final, it's always final minus initial momentum, right? Change in is always final minus your initial state. You don't have to write this down if you don't want to. So when you're looking at this, as just kind of as I work my way through, and it's probably not visible to those back there, but where we get down to is that you have the mass. Remember, doesn't change; it's a closed system. Right. So we have our change in momentum, which is really just a change in speed, because our object again doesn't change mass, is equal to your force times the time that net force acts on the object. Does that kind of make sense? Right? So like, and we're going to talk about lots of examples with this, but it's just a different way of looking at things. Right? If you move this T over, because you're like to do stuff like that, you can move this T over here, and then you're going to get VF minus VI over delta T, which we know is acceleration, because that's one of our kinematic equations. And then you get the net force is equal to MA again. So really we're just changing where the units are and the variables are to give a different way of looking at the world. Right? So it's not like we're doing something new from your point of view. It is new from your point of view. Sorry, shouldn't say that. Brand new from your point of view, but in a large context it's not much different than what you already know. Any questions so far? So the next stage of this is just we're going to look at some of the technologies that kind of go with this equation. This is obviously a big part of your project that you're going to be doing, your egg drop project. So I'm just going to rewrite this equation that I have at the bottom here at the top of the screen. All right. So, I forgot to post this online. Okay, so when we look at this equation, I'm going to put M Vf minus Vi equals the net force times target. Okay, and this is delta P over here, just a reminder. So we're going to look at 3 scenarios here. So we're going to look at technologies and actions that you do that follow this new concept of impulse, because as I said, it's the big thing for your project. So if we take a look at this screen here, we're looking at technologies or actions that you do where your change in momentum is constant. So whether you have the technology or you do the action or not, your change in momentum is going to be the same. So I'm going to let's use this one as an example first. So if you go on the expressway, next time you get on the expressway, you're getting off on, like, say, Highway 8 is a really good example to go out towards the 401. When you go down the exit ramp, the highway splits, you'll see there's a large section of yellow barrels at that corner there where the highway divides. And sometimes you see the drivers that wait to the last minute and try to cut off and almost hit the barrels on the way by. So these barrels are there to protect you. And I wish I had a video clip of how them in action. So what they do is they're filled with water or sand traditionally. And when a car is in an accident and hits the barrels, it uses this concept of impulse to keep the driver safe on the inside. So the comparison is always an object that doesn't compress and an object that does compress. So when we're comparing the 2 scenes here. So in the first scene up here, this yellow or red car is colliding into this car here. And because this car does not bend or deform in any way, if this car was going at 60 kilometers an hour before the collision, right, it goes to 0 just after the collision happens. So that's our change in momentum, right? We're going from 60 to 0 in both cases here. What's happening between these 2 cases here is that because the barrels are allowed to be compressed, they expand the time that the collision occurs, right? They're increasing the time that the change in impulse happens. And as you can see how everything kind of works up here, if this side's constant, if you're increasing the time that the collision occurs, you're going to be decreasing the forces that the occupants feel inside the car. Does that make sense? So if one goes up, the other goes down. Right? So again, looking at the cars here, right? The barrels increase the time that it takes for the car to come to a stop. Right? So it's going to decrease the amount of force that people feel inside the car. Makes it more survivable or less injury. Another example. I don't know if you've ever jumped and then not bent your knees when you land. I just cringe at that now at my age, that my knees are not good anymore. But at your age, you can still do it if you want to. So as this person's jumping in the air here, obviously he lands with his knees bent. Right? It's the whole science behind, like if you watch parkour videos or things like that when they jump off high buildings. Right? They usually add a roll to it, which also plays into this. But when you do the jumping, just sticking with what's in the video here, right? The person, right, at max height here lands on the ground. So they're going to go from the speed just before they hit the ground to 0, or it's from 0, yeah, the speed just before they hit the ground to 0, just as they hit the ground, regardless if they bend their knees or not. And if you've never done this before, you can try it. It's very painful to land on the ground without bending your knees because your body absorbs that impact. And if your knees don't bend, then all your cartilage absorbs the impact instead. It's super painful. And if you bend your knees, then your knees can increase the time that your body changes momentum, so it decreases the force that your body feels and everybody feels good. Ashley?
What's the physics behind like tearing your ACL?
The physics behind, I'll get back to you on that, but essentially that your body moves in a direction it's not designed to go, right? Because your ACL, anterior, right? And no, anterior is the outside one, right? So if you tear your ACL, that means that because it goes down to your knee and keeps your leg stable, right? You have your MCL and ACL. So if your leg goes, bottom half of your leg goes this way suddenly, or your top of your leg goes out that way suddenly, then you're going to tear there because it's not meant to be elastic going outwards.
Okay.
Yeah. Hockey, any sport that involves equipment works the same way, right? So I put a goalie pads because they're like pretty obvious, because they're just big. That's what I mean by obvious. But any sport that you might play that involves an equipment that protects you works in the same principle. Is that all of these things, right? If you picture a hockey goalie, if a hockey goalie, like in 1950 or 1940, was to stand there and take shots, right? Or you just now playing road hockey and somebody shoots a puck at you with no equipment, that puck's coming at you, it's going to go to 0 when it hits your body, and it's going to hurt a lot, right? But you wear equipment for 2 reasons, but the impulse reason is that, again, the equipment's made of foam, so when it hits the foam, you know, we're talking like milliseconds here, right? But it still increases the time that the puck takes to slow down, and that decreases the force that your body's going to feel, right? So, and yeah, so that's what we're talking about, like milliseconds here. We're not talking about like a couple seconds, because everything still happens really fast, but milliseconds make big differences, right? And if you've ever played a sport, like I play shinny in the wintertime with my kids, and they blast pucks off my legs so they think it's funny. But it hurts a lot, right? But if you wear shin pads, your shin pads absorb the blow and it keeps your leg safe. That's why it has foam everywhere, right? Right? Soccer shin pads work the same way. Helmets and biking work the same way, right? They have foam on the inside, hard shell on the outside. The hard shell also, the second thing that hard shells do is they spread the impact force over a larger area, so that also makes it small, like a smaller effect on you too. So there's two, like a double whammy, but that we're going to look at it from an impulse point of view, right? This barrier here, right? When you see on a racetrack, same thing. Cars come in at high speed. If they lose control, if they hit the barrier, all the foam over there compresses, and that just makes it safer for the driver because the collision's not as strong, right? I don't know if you guys ever play sports where you're told to take a hit, whether it's like hockey or rugby or football or soccer or whatever it might be, right? If you take your impact, you can absorb the impact, and that's what it means. You're increasing the time that the impact happens, so it's not as much force in your body, so you still have control. Are we good with this concept? Where momentum, your change in momentum's constant, your force and time are inversely proportional to each other, so if one goes up, one goes down. Right? And just as a different way of looking at it, if you have, if you were at like Fast and Furious style doing a drag race between a Honda Civic and a Ferrari, right? If both those cars touch their gas pedal for the same amount of time, 5 seconds, you can probably guess the Ferrari is going to have the higher top speed, right? Because the force of the Ferrari's engine is bigger than the Civic's engine. So even though their time is the same, the force is going to go up, and that's going to give you a bigger change. Actually, that's the next slide. Sorry. I jumped ahead there. That's the next one. Which is this one here. So I'll go to this slide first. So this one is the Ferrari one and the Civic. Again, if you have more force, right, and the same amount of time the force is applied, then you're going to have a bigger change in speed. So I just put bobsledder because it was a visual thing, right? So in the bobsled, you can have a 2-man bobsled or a 4-man bobsled, as you guys know probably. And if you have 4 people pushing the bobsled, it's going to accelerate faster, obviously, than 2 people pushing the bobsled. So again, the force goes up, time stays the same if they both push for 5 seconds. So these guys will have a higher speed once everybody jumps in than the guys will over here. Right? Cars work the same, as I said before, the Ferrari and Civic example. Braking technology works the same, right? If you have better brakes, then you'll slow down, have a bigger change in speed when you touch the brakes. Right, so in that case here, this slide here represents a constant time and a difference in force. Right, so if your time's constant, the more force, more acceleration. Which also makes sense after doing Newton's laws of motion, right? Because you know the bigger the net force, the bigger your acceleration. And if I go back a slide, for the follow-through technologies here, just following through. Follow-through means that you keep your force is constant, but your time is changed. So if your time goes up and your force is constant, then you also have a larger change in momentum, right? So if you play tennis, right, and in tennis, if you hit the ball really hard and follow through, you have a big change in momentum on the tennis ball. And if you do like a drop shot or something where you just kind of like tap the ball, then you know that the change in momentum is not going to be as good or as big, and that's called a drop shot. I put golf up here because I play golf, but same thing. If you quit your golf swing at the bottom of your swing, then the ball won't go as far as if you follow all the way through. I think this one probably makes the most sense to you, like if you had a person on a swing, right? You don't normally go up to a person on a swing and just like tap them and expect them to go hard. Normally you bend your elbows and push it a lot, right? So again, you're adding more time to your push, which causes the person on the swing to go higher, right? Yeah, I have a video on here. You can watch it tomorrow. It's a guy breaking boards. I think he's setting the world record. But when you break boards in karate, it's the same thing. Right, you don't stop your hand when you hit the boards, you follow all the way through to apply your force for a longer period of time, and you break the board better. Okay? So on this slide here, again, the time increases, the force is constant, so again, you have your time is related to your impulse. So the longer you do something or apply the force, the longer or the bigger your change in impulse is going to be. I think that's it. If I'm not, yeah. And then we just have our examples, but we'll do the math tomorrow. So everything I just said is like very important for your egg project. If your egg project, the collision part, protecting your egg, is all based on the concept of impulse. Make sure you take notes eventually, which is a big component of your project that's due next week. Today, we are just looking at some examples of momentum and impulse, and then we'll build on these starting tomorrow, where we'll look at the conservation of momentum, and then flow into Monday with 2-dimensional momentum problems. This question here, honestly, you'll never see another one like this other than your homework today, because we're always going to use the law of conservation of energy, or conservation of momentum. So when you're looking at this one here, I don't know even if it's worth writing down, because you're just typing it on your calculator, making sure you get the right answer. Right? I feel this question is below you right now because it's so easy. But try it out. Hopefully you don't get it wrong. I tried to make this one as hard as I could, because I did put it in grams. That's about it though. And our equation, if you remember from yesterday, right, P equals MV. So I'll give you 30 seconds to type that in your calculator and make sure you get that. And then we'll do the one that's actually difficult on the next slide.
It would be really awkward if you couldn't get this question right.
It would be awkward if you didn't get this question. Take your time, do it right. Okay, time's up. Next question. So this one's harder. Definitely harder. So we take a look at this one. I'd like you to read the question there. We'll go through it. There are no typos in this question either. Before somebody asks me about part B. So this one does require a system diagram and does require a little bit of work. All right, so take your moment, take your time, read it, draw your diagram. Okay, so when you drew your system diagram for this one, here's what I'm hoping you drew. You drew something that looks like this, however you drew your balls or wherever you drew them, that's up to you. But you should have a vector going eastward initially, which is towards the wall, and then a westward velocity vector afterwards. So we have our initial and our final states, just like we did with energy. In our table of values, remember that we were back in vector land. So when we do our table of values here, right, we have our mass, 600 grams. We have our initial velocity, which is 48 meters per second east. And our final velocity, we know is going to be a negative number, meters per second. Or no, we do know. Never mind, we do know, 35. All right, so our final velocity is negative because vectors matter again. And if I say east is positive, it bounces back west. So that's something you just have to catch, right? Because it's not up there. It just says it bounces backwards at 335 meters per second. I know for a fact that not all of you saw that and incorporated that in your table values, because I asked this question on tests as well, and usually 2/3 get it wrong. And they do the math right, everything's right, they just forget the negative sign there, and it makes everything afterwards wrong. So just take your time, make sure it matches up to your compass. Okay? So our impulse equation from yesterday, if you recall, was we had delta P, which is our impulse, is our change in momentum. That's one of the versions we had written down yesterday. So we can plug our numbers in, and I'm hoping we get the right answer here. And just to make life a little bit easier, right, I'll just factor out the mass, so I only have to do it once. All right, so then we have 0.6 kilograms on negative 35 meters per second minus 40 feet. And does that work out to be 50?
It's 49.8.
Pardon?
It's 49.8, so yeah.
49.8. Oh, 49.8. Alright, so make sure the negative sign stays there, unless you flip it to west, in which case that's also okay. Okay, and then for part B, we know that delta P is equal to our net force times the time. So our net force is equal to our change in momentum over change in time, which is the negative 49.8 kilograms times meters per second, divided by 25 milliseconds. That should work out to be 1992. Is that the right answer, 1992? Yeah, good. So our net force is 1992 newtons east. Hunter?
He's up there.
Sure. Any questions with that? So that's new. Take some time, digest it. Vectors again, so that's right. If you forget that minus sign for the 35, then you'll lose half a mark on a test. It's not like super huge. It's not like you're getting 0, but it's worth something to you. So just take your time and do it right. Okay, so that's the end of our note for today. So I want to give you guys time to do your homework. So when we take a look at the conservation of momentum, you don't have to write this down if you don't want to. Just kind of an overall perspective. So when we look at the conservation of momentum, why it's really important for in the study of science in physics is that it looks at collisions or things that happen very quickly where your forces are very extreme. So we're not looking at it from a forces perspective, because we could do the same thing through Newton's 3 laws of motion when you have like the football player being tackled by the other 7 or the car accident there. So you can use Newton's laws to do the same stuff that you can do with momentum, but because momentum, you can look at how the system was behaving before the collision and how it's behaving right after the collision. It makes it a lot easier to look at things, essentially. So that's why we look at momentum, because it gets rid of the forces and like the impulse that we looked at yesterday, right? The forces and time, right? They change and they're always in there. And just, as I said, just makes things easier. When we have the law of conservation of momentum, so you could write this down. For the law of conservation of momentum, it's like every other conservation law that you've come across in high school. And it's with the new property that we are focused on, though, is momentum. So when we're looking at a system of objects, so we're not looking at a single object anymore, but the system itself, the momentum of your system before your interaction, in most cases it's a collision, but not all the time, is equal to the sum of the momentum of the system after the collision. So if you play like pool, like in the pool table there, right, if you're really good with momentum, you'd be an awesome pool player because you would know where all the balls go after the collisions, be able to calculate it in your head and never miss a shot, right? And that's what the expert pool players do, right? I put a hockey player there. Sabres won their first game last night. I'm a big Sabres fan. I don't know if any of you guys are. Probably not. That's why I wore my Sabres shirt today too. Probably their only win all season though, so I'm going to enjoy it today. But same thing, we have collisions in sports. It works the same way with momentum, right? You have to have, if you're a high level athlete, you have to have some intuitiveness with momentum to make things go the way that you do. Like in soccer, if you're going to hit a soccer ball and a corner kick, you have to hit it. You can't just knock your head towards the net as the ball comes across you, because the ball sideways momentum will just keep it going sideways. So you have to hit it back in the path that it's going to negate its momentum. So the big key here though, the conservation of energy looked at a single object, right, in your problem. So from start to finish, it was one thing from start to finish. Here, it's not one thing anymore. It's a system of things. So it could be, in our cases, most of the questions will be one thing. Or sorry, two things. Whatever that might be. Colliding, interacting in some regard. But if you can do two, you can do 100. Because there's no real difference. It just adds more values into your equation. So that's why we only focus on two. Sometimes I'll go for 3. And I have one question that involves 4, but that's only if you really want to go there. So any questions with this? So you're looking at your system. So whenever you talk about the conservation momentum, you have to define what your objects are in the system. So that's something. And that the system, I don't have it up there, but your system's a closed, isolated system. So there's no energy being brought into the system. There's no forces involved that hold things in place. Right? So what I mean by that is if I run headfirst in the wall right now, that would not be conservation of momentum because there is an external force acting on that wall that's holding it there. Right? It's not free to move. Both objects, when they collide, have to be free to move. However, that movement occurs. Right? So a lot of my visuals are like pool because that's the balls can roll around. Curling is a good example. If you've ever seen curling on TV, I find it really boring to watch, but you might love it. It's a great sport to play. Have you guys ever played curling? Yeah, I got one curler. That was one of my units in grade 12 phys ed, is curling. That was a fun unit. But that, like things like that I want you to think about, right? If you play like Angry Birds on your phone, right, also follows momentum. And if you're a gamer, you really can tell games that focus on like real physics versus fake physics because of the way they handle momentum if there's collisions in the game. All right, so all right, so I put up here, there's a lot of words. So to be defined as a collision in terms of what we're dealing with, the conservation of momentum, you have to have 2 or more bodies that exert a strong force on each other in a short period of time, right? So we're looking at accidents, right, or collisions. So we're not looking at 2 objects slowly coming together and separating. We're looking for like sudden impacts between one and the other, where there's no like chance of hitting the brake pedal to slow things down before the collision. It's always right before. The second bullet there is that we always distinguish between the before and after the collision. So before and after is not like in conservation of energy where a lot of time could happen between the start of the problem and the end. We're looking at the instant before the collision and the instant after. Right? So we're not Like if you how do I want to say this? If you're out in the parking lot right now and you witnessed a car accident, you could use the physics here to figure out who is speeding and all this other stuff. That's how police officers do it when they do crime scene investigations. But what a lot of students kind of bring into place is they always say that momentum is not conserved because friction is present. Well, we're not talking about when the movement actually happens, where friction has a role in what's going on. We're looking at, again, that split second before things collide and that split second afterwards. Because friction plays a role up until the collision. Friction's going to play a role how things happen after the collision. But that moment of impact, the force of friction is so small and gravity is so small compared to the forces of the impact that they don't matter. They just don't matter. On the slide here, I did put just some pictures. I just realized one's upside down, but that's okay. So when we talk about collisions, I put the things don't actually have to touch each other. So the one here, sorry if my iPad's in the way here. Right, if you have a magnetic force that repels each one, then they're not colliding, but it's still considered a collision. Right, we have our springs here that will push them back apart. That's also considered a collision. You can have like a bullet in the wood here. The bullet could come embedded in the wood. And we're going to look at a lot of questions like that. Right, that's considered a collision. If you have two balls of different masses that collide together, that's collision. And we'll be able to predict how they speed away afterwards. And then the interaction part is something like this one here. When you have the concept of recoil. So if you have a gun, bow and arrow, in this case a cannon, where there's no momentum before something happens, and then all of a sudden you have motion afterwards, then that's not a collision obviously, but I called it an interaction. Right? Because the momentum of your bullet, you know, action, reaction, Newton's third law, where the force of the bullet, the gun on the bullet goes forward, the force of the bullet pushes the gun backwards, but we're looking at it from a momentum point of view, is that the momentum of the bullet going forward will be equal to the momentum of the cannon going backwards. So that's our action-reaction pair, and the conservation of momentum there. Right? There's always I think it's in one of your homework questions, a silly question where it's like you get thrown your friends play a prank on you, you get thrown onto a pond with just your backpack, right? Not realistic, but it works under this principle here where if you are in that situation, if you throw your backpack in one direction, your body should start to slide in the other direction, right? Your action-reaction pair, but also conservation of momentum. If you had lots of books in your backpack and you threw each one individually, it would be the same as if you threw them all at once. It's your system that's important. There are 3 types of collisions that you need to be aware of, and I'm going to differentiate between each one. So I'll give you a second to copy that down, and then I'll talk about it. And while you do that, I'm going to do the attendance. So this is the ideal collision. This is not, this is very hard to actually get to happen in the real world because, as you know, friction is always present in real world situations. In an elastic collision, so elastic is the key word here, as you can read, right, in the collision, your momentum is conserved, but so is your kinetic energy of the system, not of the objects. So the objects could change speed, but if you found the energy of the system before the collision, it would be the same as the energy of the system after the collision. Where this happens, or where scientists use this principle, is to find new particles in the electron or the particle accelerators that you might hear about in the news. So when they smash atoms together to make new elements or to see what elements are made out of, right? They use the conservation of energy and these elastic collisions to kind of figure out what's going on. Really, there's nothing that you would encounter that would fall under an elastic collision. The best example I can think of would be super bouncy balls, because they're pretty good at not losing energy when they bounce, right? When you drop them, they almost bounce to the same height. So they're pretty good. That's about it. Sometimes in pool, if you take a really good pool shot and it hits the other ball dead on, the white ball will stop and the other ball will continue on. Or sometimes you see that at a bowling alley where the ball comes out the ball return, and if there's like a ball sitting there with a space beside it, when the ball comes up to return, the one that was moving stops and the one that stops starts moving, right? So that's kind of the elastic collisions. In pool, I don't know if you guys know this, but the white ball on the pool table is actually heavier than the rest. So it does have a little bit more momentum than all the other balls. Not by much, but it's designed that way. The next one is a more real world scenario called inelastic collisions. Well, I should mention before I forget that sometimes your textbook, or if you're doing research, they might call this one perfectly elastic collisions or completely elastic collisions. So just in case you see that wording, anything that's elastic collisions with an adjective in front, they're all the same thing. It's the inelastic collisions where the adjective makes a big difference. So here you have an inelastic collision where your kinetic energy is lost in the system, but your momentum is still conserved. So this is any collision that you see where your objects separate after the collision, then it's an elastic collision. So the second bullet's the big key here, that your objects separate after the collision. So I put bumper cars up there, right? Golf, I don't know if you've ever seen slow motion golf balls being hit before, but even though they have a hard exterior to you, when they get hit by the golf club, they compress a lot. That's actually a new thing in golf, where you can look at the compression ratio of your golf ball to match your golf swing, if you're into that type of thing. I'm not, but there was a guy I played with last summer who was talking to me all about it on the whole round of the golf course.
That sounds boring.
So I learned a lot. And then bowling there. So again, going back, we are only doing 2 objects, maybe 3, if you want pain 4. But it works for 10-pin bowling. So you can do the momentum calculations, which is when you play Wii bowling, right? The Nintendo programmers do the physics to figure out where the pin should go after the bowling ball strikes, or any bowling app you would have on your phone just to waste time. Any questions with that? I just want, as a side note, I want to make you aware that when we do questions like this, we always do it from a bird's eye view down. So we're not going to be worried if the pins fly off the ground, because the momentum is not conserved in this diagram if you're looking at the pins actually flying through the air. Because what would happen to be conserved is that because you have momentum going up, because the pins are going up in the air, then you have to have an equal amount of momentum from the bowling ball going down into the ground. And we all know that the bowling ball itself does not go into the ground because it's on the floor, right? And there's that external force of the floor pushing the ball up, so the momentum can't be conserved vertically, but it can be conserved horizontally. So that's why we always look at it from a bird's eye view. So we can, like north, south, east, west, compass points, the momentum will be conserved, but not up and down. So we don't look at the up and down part. The third and last type of collision is an adjective that goes along the lines of perfectly or elastic, or sorry, completely, so something along those lines, inelastic collisions. So in these types of collisions, your two objects or more stick together after the collision. This is a key word, whether you want to highlight it or not. When you read a question, sometimes the author of the question will put it's a completely inelastic collision. So that needs to be a trigger word for you when you do problem solving, to know that the objects stick together after the collision. Because if you miss that, you will have two unknowns in your equation and you won't be able to solve it. So that just maybe highlight that so you remember. So when things stick together, that means that they have the same final velocity after the collision because they are, well, they're stuck together, so they move at the same speed. Right, so I put a car accident here. So this only applies to this accident if the two cars stick together after the collision. That doesn't happen a lot, but I put it up there. I put the baseball player there, Russell Martin, because when the ball gets caught in his glove, that's a completely inelastic collision, right? And then whenever this snowball hits this green ball, they stick together. Apparently they're not rolling, they're going to slide across. That's it. Okay, so a bug on your windshield would be completely inelastic, right? Because it sticks to your windshield after you hit it. Right, a bird on your windshield when you drive, an elastic collision because it usually bounces off. That's a very morbid example, but that's what's happening. Any questions of the three types of collision?
Well, I guess it could apply to two of them, but in pool, if you were to put a backspin on the ball and it would hit another ball, the ball would be rolling backwards and the other ball would go forward. So how would momentum work there?
It would still apply to the collision, but the spin you put on the ball adds velocity in whatever direction it's spinning in. So you would still be able to predict where the ball you're colliding with will go, and the spin doesn't really affect that ball, but it does affect the cue ball as it spins backwards or sideways, depending on what you're doing. Right? Yeah, so the moment after the collision, you'd be able to predict the direction the white ball goes, the direction it was backspin. Yeah, the direction the ball will leave after the collision, but then the spin would influence its direction too. And if it were to hit the side, then it affects how it bounces off the side too. If you put a side spin on it, but it doesn't fall, the law of reflection. Okay, I already said this, so you can skip over that. So again, just to emphasize, if you didn't write it down already and you want to make note of it, right? Momentum is not conserved if you have external forces acting on your object, right? So if you jump up in the air right now and land, right, that's a collision. But the building does not go deeper into the ground and the earth doesn't move. Because it should if it follows the law of conservation of momentum, but it doesn't because there's other forces acting on the earth, so it won't move. But if you're in space, then things wouldn't work. Jake?
What would the other forces acting on Earth be? Like that prevent it from?
Well, okay, well, Maybe if you look at the Earth's mass prevents it from moving, so it would be imperceptible. We'll go with that. Yeah, the building itself has the normal force and the force of the Earth pushing it up, so that's why it doesn't move. But if you went out to the soccer field and jumped, then it would technically move, but again, it's a comparison of mass. Yeah. So if you had even the whole world on one side jumping, it wouldn't move. That'd be crazy. Wasn't there a Nike commercial where they all ran in the same direction to spin the Earth?
Spin the Earth, spun the other way to turn back time.
To turn back time, yeah. Wouldn't that be great? I mentioned this already. I only throw this slide up here because I'll tell you now, there'll be a true or false question that's exactly like this slide. Because it's one of the random criteria, my curriculum expectations that I have to mention. So any of the study of the subatomic particles is based on conservation of energy and elastic collisions and conservation of momentum. So if you go into particle physics, you'll learn more about that. If you look, actually no, the old textbook covers had a picture similar to that one. And so you'd have like your collision over here, it spits off many different particles that make up atoms, and they spin like this because they're in a magnetic field, and we'll talk about that maybe next week. If we take a look at this question here, a small truck and a large truck have the same kinetic energies. Which truck has a greater momentum? Or are they the same? I should put that as an option too if you want to talk about that. Any ideas? Want to wager a guess? Ethan?
Well, for them to have the same kinetic energies, but the large truck to be bigger, that would mean the small truck has a greater velocity, but the large truck would have a greater mass, and in momentum, oh god, it's mass times velocity.
Yep.
Oh, but velocity squared. So
In kinetic energy.
in kinetic energy.
Yep.
So would the large truck have the bigger momentum then because its mass is greater?
Yep. It would be. All right, so if we follow his logic there, right, kinetic energy is mv squared, half mv squared, right? So your speed squared, so the mass might be smaller for the energies, but if the truck or the car is moving faster, right, the speed squared will help balance things out. And then if you look at momentum, which is just m times v, right, the speed's not squared anymore, so the truck, because it's heavier, will have the greater momentum. Can an object have kinetic energy but no momentum? And then I flipped it for the next one. What do you guys think there? Jake?
No for both of them because both of their equations have mass and velocity. So if any of them are zero, they're both zero.
Yeah. Okay, so that's where I went to. Then it's not, they both don't have velocity. What does kinetic energy use? Speed, right? So, and speed and velocity are different, right? So does that change your answer? I don't know, I'm asking you.
Probably.
I don't know. Because your momentum, right? Okay, Ethan, what were you going to say?
Well, energy does momentum use velocity because it cares about direction, but that
Yep.
kinetic energy uses speed.
Yep.
So it's something about, I can't think through it right now, but it's some case of one having a speed but not a velocity, but
Yep.
not a speed.
So if it goes in a circle.
Yeah.
Yeah. And so I went there, right? If it goes in a circle, it doesn't have velocity, but it still has a speed. Very deep, isn't it? This is a deep question. Jake, you're right. The answer would be no to both, because in both equations they deal with, the equations don't mention it, but it's the instantaneous speed and velocity at those moments that those quantities are measured. So even though velocity is in momentum and speed's in kinetic energy, then they both be zero. They're looking at like right now, what is the momentum of an object, not over a large period of time. How does its momentum change? And they're instantaneous. I did notice on your test, for those you're curious, I know there was one question where the airbag question, right, where the person jumped on an angle, right? Again, kinetic energy is a scalar quantity, so angles don't matter. So for those who ask me questions like, is it up or is it down? It doesn't really matter because the angle doesn't play any role in the question itself. All right, so here are some examples. So I have a bunch of them. I'm just double checking. Yeah, I do have a bunch of them. I did 4 different ones. They build towards the grand finale of number 4. They just get more and more difficult in terms of there's just more numbers involved in each one. The actual math I find is not as hard as like forces. I find forces really hard in our class. This isn't at that level, but it might be for you because it is new. I need you to pay attention though to how we solve these problems. Again, you need system diagrams. You need to have the right notation. Good table of values is always helpful. And there's no energy transformation equation or free body diagram business this time, so there's less drawing involved, but that doesn't mean there's less thinking involved. So you can read this one here. Ethan shoots a rifle at a target. Find the recoil velocity of a 1.9 kilogram rifle if a 30-gram bullet has a velocity of 750 meters per second forward after being fired. All right, so okay. Okay, so for all the questions, or most of the questions you're going to see, right, you're going to have 2 objects. So the first thing is to draw 2 objects. And you can see here it's a rifle and a bullet. So we're not going to get like too technical here. I'm just going to draw this. Here's my rifle, chamber, and the bullet. Something pretty basic like that. Okay? And there's nothing happening, so that's all the picture represents there. Okay? Afterwards, we have our bullet. How do I draw? We're going to have to talk about how we're going to do our writing too. Your diagram has to have some components. It does not have to look like mine. I'm sure there's better ways to draw this. You need to have 2 things. You need to have, or 3 things. You need to have a before picture and an after picture. So you need 2 separate pictures. That's number 1. So that's why I have my before or initial, right? So here's my initial, and it's my final. All right, so I have an initial picture and a final picture. In the initial and the final picture, I need to have the objects of the question and their velocities indicated. So actually, I haven't read your textbook in this part yet. So I'm curious as to what they do for this. And on the old textbook, they use a different notation. Bear with me here. Yep, they switched their notation. Perfect. Okay, so I have VBF. So we have velocity of the bullet final. And we have VRF, velocity of the rifle final. Right? And if we had initials, we would have eyes in the top picture. And the last thing is obviously we need a compass system because we're back with vectors. Compasses are important. Alright? So diagram has the picture, the vectors, and compass. Okay? So we're not dealing with any other kinematic vectors in any of these problems. They all kind of look the same. And however you want to draw that information, that's up to you. The next thing is the table of values. There's different ways to do this too. So I can do the mass of the rifle is 1.9 kilograms. Mass of the bullet is 30 grams. This is where it might look a little weird to you. So we have our table of values that has 6 things in it. So all of our conservation of energy questions today will have 6 variables in them. If it has 2 objects, there's 6. If there's 3 objects, there will be 8. Because every object has an initial velocity and a final velocity. When we go to 2 dimensions, everything will have 4 velocity vectors. The initial and the final in the x direction, the initial and the final in the y direction. I mean, yeah. So it just gets ridiculous. But that's what we're doing. So that's our table of values. You should look the same every time. Don't think too hard. That's what it is. Obviously, the subscripts change based on your questions because you're not always dealing with rifles and bullets. But the math is the same. Or the setup's the same. The actual math itself, as we go through this, right, we're going to say, just like we did before, we're going to start with our law here. So we have the momentum before is equal to the momentum afterwards, right, lowercase p's. So we're going to state our law that we use, just like in energy, we stated the law of energy we're using. The next line should be the same for every question. And again, it's a long version, which you see this one. This is the topic I always dread because it's just really long. The subscript order doesn't matter, just in case you're wondering why I have something backwards from before. So we have this line here. So you have the momentum of both objects before. Remember, the system's momentum is constant. So your system's your system's momentum is constant. So you have both objects. If you had a third object, you just add it to both sides. If you had 100 objects, you'd have 100 on one side and 100 on the other. All right, so you're just adding to this line. That's why if I said you can do 2, you can do 10, you can do 100, because it's just adding right here. So we have the rifle and the bullet before, the rifle and the bullet after. Okay? The next step here is the thinking step. So these first 2 steps here are like automatic steps. No thinking should be involved because that's just what you're going to do. This is where the crossed out phase happens. Like, what do you not actually need to solve this problem? So my question to you is, what do you actually what don't you need to solve this problem? Ethan?
The initial initial velocities.
Yep, good. So initially everything disappears because there is no velocity initially. So we can cross that off. Okay? And then if we rearrange, because we're trying to find the rifle, right? So if we bring this over to the other side, it becomes negative BF V BF divided by MR. And then just take your time to make sure the numbers all go in the right spot. This time is not super hard because they're distinctly different objects, but sometimes you have two cars in the problem. And I've seen students use the wrong math at the wrong time. Does that make sense how that flows? So whenever, like if we go to the next question here, right, and I go obviously there for payment. But if we head off to this other question, right? You have to make sure you follow the directions because it's easy to lose a negative sign, right? And you have to, like, to get your system diagram, if you want it kind of right, you have to, like, use your intuition, right? So if we're reading this question here, Maddie is running towards her brother, right? They're running in different directions. But based on Maddie's stats up there, she's going to have more momentum before the collision. So probably the pile afterwards is going to go in the direction that Maddie was running. Right? I'm not saying it will, but you know that would be a good guess. Right? The larger object usually dictates what happens after the collision. All right, so I'll go through this one with you, and then what type of collision is this? Right, over 3 types of collisions. It's a word answer, not a math answer. Well,
Perfectly inelastic.
yeah, good. Completely inelastic, right? Because they stay together after the collision. That's the key word there. And then we can calculate their speed after impact. And see what we got. I have no idea what you would draw. So I drew Maddie tackling her brother, picking him up, and after the collision, they're probably going backwards. You can also do the same thing with blocks, if that helps you out. Blocks would do the same thing. You don't have to be artistic. I'm not a good drawer, so that's the best I got. I'm gonna say south is positive because as I'm guessing, Maddie had more momentum than her brother. So I'm gonna say south is that way. All right, so anything going north will obviously be negative when I make my table of values. So here we go. Same table of values as before. We have the mass of Maddie, mass of my brother. Space. Okay, so we know each person's speed beforehand. We know that they stick together, so their final velocities will be the same. Right? And then it's just going through the same steps we did before. The math will look a little different when we get to the simplifying level, because each time we do that unique problem. Here we go. All right, so we have the first two lines, I'll get written right away on the page. And then we have to think, how can we make it easier? What are we going to simplify? There's two things we're going to change before on the next line. We have to get rid of one, or no, we don't get rid of one thing. So we only change one thing actually. What can we change before we get to the next line? And yes? Jake?
You can change the last part to 2 times any one of them.
Yeah. 2 times? It's not 2 times though.
But if they're the same for the final,
Their masses are not the same. Yeah, you're right. So we know the speeds are the same here, right? So that's a common factor in both the last terms there. So we can common factor those out. Right, I could, just so you can see it, if I keep this same, and over here, and I just change the brother's velocity to Maddie's velocity because they are the same, just to give you the visual of that. And then now you can see that it is a common factor, and this happens most of the time. If the objects stick together, right, so you have the common factor out of the masses. Yeah.
If you wanted to like show that on a test or something, but you didn't want to keep writing on the left side, could you put the same as above marks to save time?
Yeah,
On the
sure.
left side? Okay, good.
Yeah, I'm okay with that. Other people may not be. So don't say, well, Mr. Arkell, let me do this.
Yeah.
All right, and then we just move the bracket to the other side. Which I'm going to just switch sides so my equal signs will always line up. Alright, so I just brought the brackets to the other side, even though it doesn't look like that because I also flipped left and right sides. Just because I want my equal signs to line up and it's easier to write all the numbers afterwards. Talk about a long question. What we got? 97. Okay? So conservation of one momentum is the same, right? It's the questions are obviously going to change, but the process is, I don't find like the problem solving process as difficult as conservation of energy, because in those questions you had to figure out what energies were involved. Here, there's less thinking because it's just the momentum. If you have 3 objects, you just literally add 1 more on each side, as I mentioned. And then it's just a matter of making sure your negative signs and then numbers go in the right spots. Right? So, that's it. Any questions of that? Does that make sense? Are we good? Yeah, so, like, I do have more questions. I don't want to bore you, because as I said, they are pretty repetitive. All right, we have this one here with Andre and his brother. I actually saw this one, so I had 1 year where the students made videos of the physics concept in this unit, like the other 2 units. And I had a set of identical twins, and they did this, because their masses were the same to run at each other with yoga balls. And it was a disaster. I don't know if you've ever seen YouTube videos of yoga ball fails. But it is quite an elastic collision. If you're not ready for it, that it didn't go well. Because the one guy, just before the collision, he chickened out, the guy who didn't have the ball. So his momentum went from equal to his brother's to 0 if he stopped moving. So his brother just cleaned him out with the hit. But yeah, so you can try this one. And then the last one I put up there too. It's the same, they're all the same, like there isn't much variety. So feel free to do one. I'll put both on the same screen actually. In this case here, the only reason why I put this one up here is because the balls obviously separate after the collision. So to figure out the type of collision it is, you have to calculate the kinetic energy of the system before and after. So the 1/2 mv squared for both objects added together compared to the one afterwards. And if the numbers are pretty close, like you think it's a rounding mistake that makes them different, then it makes it elastic. And if it's a difference that you know is not a rounding error, then it's going to be an inelastic collision. So that's the kind of the one that differentiates it there. Okay? So I'll put these both in the same slides, but that's it for conservation of momentum and the types of energy. So you can try these. The homework's on our homework page 2. I'll put that on the same slide. You have 10 minutes left to do whatever you'd like. If you want to try, I try one on your own just to double check you can do it on your own, because things always look easier when I do it. So we'll do the first example here, which is an explosion of stuff. I just put a balloon blowing apart. It doesn't really work this way, but I thought it'd be less violent than something else that could explode. So we'll look at this, and then we're going to go into completely inelastic collision, which is the next level of difficulty. And then we're going to finish with an inelastic collision, which is the hardest one. So each one is going to add just more work to it, but the process will be the same from start to finish for each of them. So you can read this question here. We have an inflated balloon that blows apart into 3 pieces, and we want to find the velocity of the third part after the explosion. So this is also kind of new to us because we haven't worked with 3 objects yet. We've only dealt with 2. So we're just doing 3 just because. And we're going to work